Okay. All right. So review. Now, suspiciously, there's a lot of blank space here. We'll get into why there's blank space later on in the lecture. But these are some things that I expect you to know. And in particular, when it comes to the two midterms, they're not cumulative in the sense that things that we did on the first midterm, I'm not going to test you on the second midterm. So for instance, I'm not going to ask you to find a tangent line. I might say find a local linearization, which is essentially the same thing, but I'm not going to say find a tangent line, because tangent line is the first midterm. There's no limits, not even for horizontal asymptotes. Nothing. The word limit does not show up anywhere on the test or in the answers. It's the only stuff that we've covered. Now, the only two things that well, maybe not two. The only things from the first midterm that I expect you to know are the fact that if you take the derivative of a sum of two functions, it's just the same as just taking the derivative of each one individually and adding it up. If I take the derivative of a constant of a function, it's just the constant times the root of the function. And the product rule, derivative of a function f times a function g is f prime g plus fg prime. And of course, the other one is the derivative of x to the power a is ax to the a minus 1. Those are pretty much the only things from the first midterm that you have to know for the second midterm. Everything else is what we've covered since then. So what are some things that we've covered since then? Well, we've covered the chain rule, which is the derivative of a function g inside a function f. So the derivative of f of g of x is f prime of g of x times g prime of x. We also did sine. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of secant is secant times tangent. And of course, this one, derivative of arctangent, is 1 over 1 plus x squared. You can bet that on the midterm or the final, you will see arctangent, possibly both. I haven't written the final yet. But, so you should know this one. In fact, you should know all of them. I should tell you. You shouldn't say, oh, I don't need to know the rest. You should know this one. And then finally, I wrote one other thing down which will come in useful later on today. We didn't do this last time, but we did this a few lectures ago, where we had a corollary to the mean value theorem. And this corollary said, if the derivative is 0, not at a point, but it's identically 0, 0 for all values of x, then your function is a constant. This fact will come in useful for what we talked about today. Now, what we talked about last time, after we drew some pictures for graphing, we talked about optimization. So optimization, our goal is we're trying to maximize or minimize something, some value. How do we do it? Well, the first step is you need to find appropriate labels. Now, oftentimes it helps if you can draw a picture. I like drawing pictures, and so whenever I can, I draw a picture. You can't always do that. Now, what are the appropriate labels? Well, we're trying to label some variables, and so some questions to ask is, what is it we're trying to optimize? Whatever we're trying to optimize should have a name. So maybe we're trying to find the maximum area, maximum volume, maximum profit. Whatever it is we're trying to maximize, that better have a variable name. The other thing that should have a name is things that we can vary. So for instance, if, say, I want to maximize the area of a rectangle, the variable names might be the lengths of the sides. I'm not going to give variable names, to things which aren't important. If I'm trying to maximize the area of a rectangle, I'm not going to give a variable name to the temperature, because that has nothing to do with the area. Only what counts into the problem. That's what we label. So once we have our labels for our variables, the next step is almost always the hardest step, and it's to find a function for what we are trying to optimize. So we're trying to optimize something. So we need to find a function in terms of these variables that we can vary. Oh, varying variables. Oh, that's good. And there's one little trick. We might have several variables. So for instance, for a rectangle is usually base times height. Well, that's two variables. But we're a single variable kind of class. We love a single variable calculus. So we need to get down to a single variable. And how do we get that? Well, usually if there's more than one variable involved, there's some kind of a constraint on them. It's not that the length and the width are arbitrary. Maybe they have to add up to some proper number. And that's a constraint. So we use that constraint to really get us down to a single variable. So we have a function which expresses what we're trying to optimize in terms of a single variable. And now we just go crazy with our awesome calculus tools, and we find the max and the min. OK, so we have a few minutes to do one. All right. So here's an example of a problem. You might start out with a flat piece of cardboard. And I'm going to do the dangerous thing and just make numbers up. Usually when you just make numbers up, you get into trouble. Let's say it's 10 inches by 8 inches, a small piece of cardboard. And what you want to do is you want to turn this piece of cardboard into a box. The way you're going to do that is essentially you're going to cut out corners. And then after you cut out the corners, you're going to fold it up, and the end result will be a nice little box. Okay? So imagine, cut the corners up, fold it up, tape the corners, tape the sides of the edges together. So here's a question. What is the maximum possible volume of my box? Now, of course, depending upon how big I cut out the corners, I get different sizes of the volume. So we need to find some appropriate variable. Now, how do you calculate the volume of a box? Yeah, length times width times height. So in terms of, what are we trying to optimize? Well, we're trying to optimize the volume. What can vary? The length, the width, and the height can vary. So I have that the volume is length times width times height. So in some sense, this is like the first step. We know what's going on. We're trying to optimize this volume in terms of these variables. But of course, I have 3 variables here. So I really don't want to get 3 variables. I want to get down to a single variable. Well, let's think about what's going on. Well, how big is the height? The height is really this same length here. It's that height I'm going to fold up. So this length is the height. And this length is the height. So what is this length here? Well, it's a total length of 10. Well, it's still a total length of 10 up here. And I took out h, and I took out h, so what's left is 10 minus 2h. Now, what if I came to this side and did it? So the total length here is 8. But I cut out h here, and I cut out h here. So this length left is 8 minus 2h. So in fact, I can take this volume, which is the length times width times the height. The height is really the size of the corners that I'm cutting out. I can replace length and width by 10 minus 2h times 8 minus 2h times h. OK, now we've got volume as a single variable h. And we can replace that h by x, but it doesn't really matter. It's just a name. Now, before we go to our next step, because essentially we've done the second part here. Our last step is really just use calculus and go crazy. Before we do that, before I take a derivative of this is looking kind of ugly. What can I do to make it simple on myself when I go to take a derivative? Yeah, I can do what's called FOIL. Or, if you like, expand. And so the idea, of course, is oftentimes in calculus, the real trick is before you start going crazy, step back for a second and say, I wonder if I can make this a little bit easier on myself. And if you can, you do it. OK, so if I FOIL, and then really what I'm just doing is multiplying it all out. You can call it distributing if you like. So if I do that, you get 80 times h minus 20h minus 16h. That's another h. That's minus 26 h squared minus 2h times minus 2h times h would be plus 4h cubed. And of course, I should point out here, what do we know about h? How big can h be? There's another constraint I haven't written down. What's the smallest h could be? 0. In other words, I don't cut anything out. It's a really lousy box. It has no height. What's the largest h could be? Well, the largest h could be was if I went crazy and cut out these really massive, huge corners like this. And then what would happen is I'd have like this. Essentially, I've cut out this whole side here. Now, how big are the corners I've cut out? It's half the length of the side. So 4. So really, I should say this is an optimization problem where we actually have boundaries. But of course, 0 and 4 are, again, really crummy boxes. So we know it's going to be somewhere in between. Should it be 36 and not 26? Probably if you're better at math than I am. Yes. All right. So now we know we're looking for an answer between 0 and 4. There really has to be something between 0 and 4, because 0 is obviously 0 volume, and 4 is 0 volume. And we know the answer isn't 0. OK. So now we take our derivative, v prime, 80 minus 72h plus 12h squared. And what do we do with this? Well, we find the critical points. Now, in this case, derivative is always defined. So the only critical points, of course, will be when the derivative is 0. All right, we'll move this down a little bit. OK. This is why I should have planned ahead. OK, all right. We probably won't finish this one. But let's talk about what you do from here. What would be your next step? See, the trick is, if you just make numbers up, you always end up with really bad expressions like this. We can do it, but I don't want to spend 20 minutes in class working through it. What would be our next step? So here we have a quadratic. Is there some kind of formula for quadratics to help us find the roots? Yeah, there's a quadratic formula, right. And when you can factor out, like, they all have 4 in common. So this makes it easier. So, for instance, this is 4 times 20. 72 divided by 4 would be 18h plus 3h squared. But then you have to try to factor that. And if you can't factor, most of the time you probably can't add if it's just a random thing. Then you would use the quadratic formula for this. So you'd end up with something like h is negative b, which is 18, plus or minus the square root of b squared. 18 squared is, yeah, I don't know either. We'll say 264. Well, why not? No, 264 is not right. Let's see, it's 180 plus another 80 is 260 plus another 64. So that's 324? Someone who's really good or has a calculator, one of those two. OK, so 324 minus 4ac. So 4 times 20 times 3 is 240, all over 2a, which is 6. And 324 minus 420 is 84. And so what's our answer turn out to be? Well, it's going to, well, OK, anyways. So you figure out which one of these is between 0 and 4, and there's your answer. One of them will be between 0 and 4, one of them won't. OK. And that's the h that you cut out, and then you can find the maximum value. Again, it's because I chose lousy variables. So that's the flavor. I'm sorry. I should have planned ahead and picked good numbers here. Yes? Well, you could theoretically say cutting out 0 is, it is a possibility to cut out 0. It's just like, the lazy man's box. It's just like, it's now not really a box. It's more like a platter of some sort. So you could say it's just strictly between 0 and 4. I mean, in terms of the problem, it doesn't make any difference. 0 and 4 are definitely not the answer, so it doesn't really matter. You just know you're looking for a number between 0 and 4. And if you go through and work it out, you'll see that one of these two numbers is not between 0 and 4, and one of them is. So the one that is the one you keep. Yes? 0 and 4? Well, it's just from the problem. So how did I get 0 and 4? So I looked at the problem and said, well, what can I say about h? H is how big the corners are that I cut out. What's the smallest corner that I cut out? Well, the smallest corner I cut out is I do nothing. And then I charge the government $100. That's the smallest one I cut out. In other words, my piece of cardboard box, my box, if I cut out 0, went to this kind of box here. It's just flat. It's nothing. And I can't cut out a negative corner because it's a length. I can't have negative lengths. So 0 is certainly the smallest. Now 4, well, what's the biggest? Can I cut out something that's 10 inches on a side? I can't cut out a corner that big because it's bigger than the length of this side. I can't cut out a 10 by 10 corner. So the question is, what's the biggest possible corner I can cut out? Well, the biggest corner I could cut out is if I cut out exactly half the length of this side. Anything bigger, it's impossible to cut out. For instance, I can't cut out a 5-inch corner here and a 5-inch corner here because there's overlap. So it comes from thinking about the problem. All right. Okay. And there's an example of optimization on one of the practice midterms. Oh, I shouldn't have said that. Okay. I don't want to give it away. You should try the practice midterms just like it's a normal midterm. There may or may not be an optimization problem on one of the practice midterms. And there may or may not be an optimization problem that is totally awesome on the real midterm. Okay. All right, so we need to go actually to our next topic because I want to make sure to cover it today. So our next topic is antiderivatives. Now, what are antiderivatives? Well, probably when you think of the word antiderivatives, you probably have a picture of something like this in mind. People are just really mad at derivatives, and so they're protesting. No more derivatives. Take love, not derivatives. That kind of thing. I have a sign, plus minus. Okay, so. All right, but no. That's not what an antiderivative is. An antiderivative, don't think of this as like you're opposed to derivatives. It's just the opposite of a derivative. Okay, so what do we mean by the opposite? Well, originally we started with a function, and we took a derivative and got a new function. So the antiderivative is we say, okay, we have a function. I'm trying to find a function. When I take that derivative, I get the original function. So in other words, we say f of x, capital F of x, is an antiderivative of little f of x if, when I take the derivative of the capital F, I get little f. So in other words, when we're talking about antiderivatives, we're looking for the function whose derivative is the function we want, or the function we're given. So we're given this function, little f of x. We're looking for the function capital F of x, so that this is true. Now, we could probably do this in some very simple cases. So let's see, what are some simple functions we can do off the top of our heads? All right, well, let's try this function. Suppose I say little f of x is 2x. And we've seen a function before where the derivative of the function is 2x. Does anybody remember what that function is? Yeah, capital F of x could be, for instance, x squared. Because if I take the derivative of x squared, I get 2x. So in this case, we'd say x squared is the antiderivative of 2x. Are there any other functions that we've seen that have a derivative of x squared? Yeah, I could also do something like f of x is x squared plus 5. Because if I take the derivative of x squared plus 5, the derivative of x squared plus 5 is, again, 2x. Because the derivative of 5 is 0. In fact, any constant I add to x squared is, again, going to be an antiderivative of 2x. So when we talk about antiderivatives, we have to use the word like and not the word the, because there's more than one. There are infinitely many. Now let me ask you this. Can there be anything else besides this function, x squared plus c? That's an antiderivative of 2x. Or is that the only kind of way I can get an antiderivative of 2x? Well, people who probably have had calculus before know the answer to this. And the answer is no. There's nothing else. Every possible antiderivative of every possible antiderivative of 2x looks like the form x squared plus c. And so that's our first result. We'll call it a theorem. And it says that if capital F of x is an antiderivative okay, of little f of x, then all other antiderivatives of little f of x are of the form capital F of x plus a constant. So if you have one antiderivative, you actually have all your antiderivatives that are possible. Because the only other possibility is you just add a constant to it. Now, how do we prove this? Well, let's give a sketch of a proof. So suppose g of x is also an antiderivative of f of x. Okay, one of the bad things about antiderivatives is a very long word, so it takes a long time to write down. So g of x is an antiderivative of f of x, and capital F of x is an antiderivative of f of x. Now let's take the derivative of capital F minus capital G. And let's see what we get. Now, one of the rules that we have about derivatives is that when we're taking the derivative of a sum or a difference, I can break it up. So I can take it as the derivative of capital F of x minus the derivative of capital G of x. But what do we know about capital F of x? Capital F of x is what? It's an antiderivative of little f of x. So if I take the derivative of an antiderivative, where do I end up at? I end up back where I started. So the derivative of the antiderivative is just the function that you started with. Okay. What do we know about the derivative of g of x? It's also f of x because it's also an antiderivative of f of x. And what is this? 0. So I know that the derivative of capital F minus capital G is 0. Now, what do we know about functions with derivative of 0? Yeah, oh, hey, look, check it out. We have this great corollary here, which says if your derivative is 0, you're not very interesting. You're just a constant. So that tells us then that capital F of x minus g of x is really just a constant. So in other words, two antiderivatives only differ by a constant. That's what that theorem is saying. Okay. All right, that's good. First result. Now, let me do some notation here. Okay, put this up. Put this down. So, some notation. Because we don't want to keep writing antiderivative of f of x every time. We want some shorthand notation. So the way we're going to write it is the following way. This symbol here, which we haven't talked about yet, but we're going to start talking about it in the next chapter. F of x dx is capital F of x plus c. And this notation simply means here, this is the antiderivative of f of x. And I should say it's a general antiderivative of f of x in that you want all possible ones. So what is capital F of x? Well, this is just some antiderivative. This is just find one, any antiderivative. So you find one, and then you say, well, to get all possibilities, you add c to it. So capital F is like one specific antiderivative, and then we find all general antiderivatives by this. So you might be wondering what this notation is, and it's sort of giving away many secrets about what's to come. But this notation comes from the integration theory. And this is a big letter S. So if you were to squash it, it would look like this. Which, if you then add the TEVEs, you get my name. So it's always easy for me to remember. But, whatever helps you. this is called indefinite integral, or indefinite integration. And again, integration is what we talk about in the next chapter, because we really are talking about two topics this quarter, differential calculus and integral calculus. So this is starting to do our segue into the second half of integral calculus. Now, the moral of the story here is that we learned all these great rules for derivatives. And so we can use a lot of the same rules for antiderivatives. And in fact, rules for derivatives become rules for antiderivatives. So here, what I really wrote down at the very beginning of class were rules for derivatives. Okay. So this is also a rule for derivatives. Now let's just think about what the corresponding statement for antiderivatives is for each one of these. Okay, now some of them we won't get to today. In fact, one of these we won't even get to next quarter. Okay, this says when I take the derivative of two functions f plus g, it's the derivative of f plus the derivative of g. What's the corresponding statement? Well, the corresponding statement for antiderivatives says if I'm trying to take the antiderivative of two functions, so f of x plus g of x dx. So here I'm trying to find the antiderivative of f plus g. What do? I find the antiderivative of f, and I add to it the antiderivative of g. So in other words, whenever you see addition, you can just break it up and just break it into smaller problems. Now the next rule, this says if I have a derivative of a constant times my function f of x, the derivative of that is that same constant times the derivative. So in other words, I can basically pull constants out in front. Now this is going to translate into a rule for antiderivatives. It says if I'm trying to find the antiderivative of k times my function f of x dx, again, I can pull the k out in front. So this is k times the integral of f of x dx. So constants come out. This is the product rule, which translates into a really cool rule called integration by parts, which we will not learn this quarter. But you will learn that in the next quarter. It's a very useful fact. So this is not for our class, unfortunately. The next rule is the chain rule, derivative of f of g of x, which is f prime of g of x times g prime of x. This translates into probably the single most useful rule for integration, which we won't learn until the next chapter. This is called substitution rule. So this rule probably is the most important in terms of antiderivatives. It's also one of the most important rules for derivatives, which is why I hope if you only remember a few things, one of the things you remember this quarter is the chain rule. Okay, so those are some basic rules. So in other words, we can, mostly right now, we just know we can break up over addition and pull out constants. Okay. Let's think about here. X to the a. This is a really important one. Suppose I want to integrate x to the a. So I'm trying to find some function so that when I take a derivative of x to the when I take a derivative, I get x to the a. Now, if we think about it, what happens? Well, I start with whatever I'm integrating. I bring the constant down, and I subtract 1 from the exponent. So whatever I end up with, it probably has to look like something where I have x to the a plus 1. Because if I think about what's going to happen with my derivative, when I take the derivative of this, I'm going to bring the a plus 1 down. And then I'm going to subtract 1 from a plus 1. If I subtract 1 from a plus 1, I end up with a, which is what I want. So it probably has something with x a plus 1. Now, the question is this right? Well, it's almost right, because if I bring the a plus 1 down, if I try to take the derivative of this, I would get a plus 1 times x to the a plus 1 minus 1, which is x to the a. So it's almost right, except I have this extra a plus 1 term. That's OK. I can fix that. I'll just divide by a plus 1. And that takes care of my problem. So if you check now, if I take the derivative of x to the a plus 1, the a plus 1 comes down, and now these cancel. then it becomes x to the a plus 1 minus 1, which is x to the a. So one way to always check a rule for derivatives is you just say, OK, if you're not sure if this is the right antiderivative, just take the derivative of this side and see if you come back with x to the a. If you do, then you're good. Now, on a side note, when does this rule not work? Is there any value that says, I'm very iffy here? Yeah, this isn't going to work when a plus 1 is 0. So there's always a little caveat. What do you do for the function x to the negative 1 dx, which is the integral of 1 over x dx? And this is chapter 7. Now, in case you're wondering, we stop at chapter 6. So you guys are going to have to wait for 2 months in suspense. Oh, what's going to happen? You're just going to, it's going to keep you up at night. I know. But, OK, so we're not going to worry about that case. So we're never going to encounter the case when I have x to the negative 1. OK, now let's come down to here. The derivative of sine is cosine. So what does that tell me about the integral of cosine? So what function, when I take the derivative of it, gives me cosine? Sine. And then we always add our constant. Derivative of cosine is negative sine. So what function, when I integrate, so I take the antiderivative of sine, what function do I get? Yeah, here I get negative cosine. So this is one of those things where it's always fun to mess people up. Because when you take the derivatives, it's the derivative of the sine is the positive cosine, and the derivative of cosine is the negative sine. But when you come to antiderivatives, it's exactly reverse. The integral of cosine is now positive sine, and the integral of sine is now negative cosine. OK. What's the antiderivative of secant squared? So I'm looking for a function where I take the derivative of it, gives me secant squared. Aha, I have it written down here. It's tangent. What's the antiderivative of secant times tangent? Well, what function when I take the derivative of it gives me secant times tangent? Well, it's the derivative called secant x. So every single rule that we wrote down for derivatives has a corresponding rule for antiderivatives. In fact, we have one more that we wrote down. The derivative of arctangent is 1 over 1 plus x squared. So what's the integral of 1 over 1 plus x squared? I'm sorry, the antiderivative, or indefinite integral. Yeah, it's arctangent. Just think of, since the derivative of arctangent is 1 over 1 plus x squared, then the antiderivative of 1 over 1 plus x squared has to be arctangent. Plus c, yes. Now, of course, I haven't written down all the functions that we possibly could write down. You might say, well, Steve, what's the derivative of tangent? OK, you can find it. You'll have to wait till next quarter to find out. What's the integral of secant? Oh, great one. I love that one. Can't tell you yet. Have to wait till next quarter. I can tell it to you, but then I'd have to give you an A. Yeah, OK. Then you may say, OK, what's the integral of e to the x squared? And I'll say, ooh, that's a good one. I don't know. And it turns out that it's sort of counterintuitive. We have all these great rules for taking derivatives. And right now, assuming that we're comfortable with these rules and we're confident in our skills, you give us any function, we can find the derivative like that. Oh, maybe a couple steps. But, we can find the derivative. Antiderivatives are actually pretty hard. And it takes a lot more effort to find them. OK, so let's see. Let's do some practice here. So we have all these fun rules. Let's see if we can do some fun problems. OK. Let's see. Da, 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 da. Oh, my notes say make stuff up. Oh, that's not very convenient. All right. So suppose I ask you to find the following integral. Square root of x plus x negative 1 times x plus x squared. Oh, let's throw in some constant. X plus 2x squared dx. Suppose I asked you to do this. And you look at this for a second and say, wait a second, we don't have any kind of rules for that. You might be thinking to yourself, well, wait a second, here I have a product. Maybe I should use the product rule, but why won't we use the product rule? Where does the product rule fit in? Product rule fits in for differentiation, not for integration or antiderivatives. So there's no product rule, unfortunately. There is kind of a product rule. It's called integration by parts, but you won't learn that until next quarter. So this doesn't seem to really fit into anything we've done up here. That's OK. That often happens. That you start with a problem, and it doesn't quite match anything that you've seen before. We don't have to worry about that. All we have to think about is, OK, if I haven't seen it before, let's try to make it look like something I've seen before. So how can I rewrite this to make it look like something I've seen before? Yeah, I can FOIL again. Now, in case you're wondering what FOIL is, if it's been a while, FOIL just means to expand out. And it stands for first terms, the outer terms, the inner terms, and the last terms. So the first terms are square root of x times x. And one of the things you should always do, even before we start doing this, is you should replace square root of x by x to the half. It's always good to replace anything like a square root sign by x to the 1/2 sign, because that makes it fit in much easier when we come to using this kind of a rule here. This rule is really written for x to a power. All right. So I multiply the first two terms together. I do that. X to 1/2 times x is x to the 3/2. That's the first terms. The outer terms, 2 times x squared times x to 1/2. Well, that'll be plus 2x to the 5/2. X to the negative 1 times x. Well, that's pretty easy. That's just 1. And that's the inner terms. And finally, the last terms, x to the negative 1 times 2x squared is plus 2x dx. Now, what we've done so far is actually nothing to do with anti-differentiation or integration. I'll probably start saying integration more than anti-differentiation. It's just easier. All we've done is rewrite it. But that's made it tremendously easier on us. Because now the next thing is we say, OK, I can use this rule that says if I have two things where I'm adding them together, I just have to do them separately. So instead of thinking of this as one big problem, I'll think of this as 4 little problems where I have to do the integral of x to 3/2 dx plus the integral of 2x to 5/2 dx plus the integral of 1 dx plus the integral of 2x dx. And now we just start working on each one individually. So what's the integral of x to 3/2 dx? So before, when we talked about derivatives, we said the derivative of x to the a is you bring the a down and you subtract 1 from the power. Now it's kind of the opposite. Now what you do is you take the power and you add 1 to start. So we start with x to 3/2. You add 1 to that. What do you get? You get 5/2. So you take x to 5/2, and now you divide by your new power. So you divide it by 5/2. So that's the same as multiply by 1 over a plus 1. Now the 2 is a constant, so I could just do the 2 on the outside, so plus 2. And again, I'm going to do the same trick. So the rule says for integration, you take your power, you add 1, 7/2. And then you divide by your new power. So you divide by 7/2. Plus the integral of 1 dx. Well, what's the integral of 1? You can think of 1 as the same as x to the 0, if you like. And then if you add 1 to the exponent, you get x to the 1 over 1. So the antiderivative of 1 is now x. And the antiderivative of 2x, well, we already saw that. That was x squared. And finally, at the very end, we put a constant. Now, you might have said, wait a second, did we need to put a constant on each single one? Did we need to say x to the 5 halves over 5 halves plus c, plus 2x to 7 halves over 7 halves plus c, plus x to 1 over 1 plus c, plus x squared plus c? Why did we just put a single constant? Well, this is the beautiful thing, is that if you add a bunch of constants together, what do you get? You get a constant. So instead of writing it down 4 times, we're saving ourselves this wonderful dry erase marker and just writing it once. It's conservation. Okay, and this is pretty much it. You'd get full credit for this, but you can make it a little bit prettier. For example, 1 over 5 halves is the same as 2 fifths, x to 5 halves. Then 7 halves I can bring up as 2 sevenths, so times 2 is 4 sevenths, x to 7 halves, plus x squared, plus c. Okay. So there's an example of a problem that you might see. Now, another thing that you might want to do is you might be told something. So along the lines of the following. You might say that I know that dy dx is 2 secant squared x. And I also know that if I plug pi force into my function y, that I got 1. And I want to ask you the question, here's my question, what was y? What function y gave me these two facts? And it turns out that if I know what the derivative is, and I know what it is at a single point, what the function is at a single point, that's enough for me to answer this question. Now here, if I just know this fact, can I say what y is in general? Well, I know that the derivative of y looks like this, and so I say, okay, well y is really going to be some antiderivative of 2 secant squared x. Now the 2 comes out, integral of secant squared x. Then do we know what the antiderivative of secant squared x is? Yeah, it's 2 tangent x plus some constant c. So just the fact I know what the derivative is isn't enough for me to say what y is, but it tells me that what y looks like. Y has to look like something in the form 2 times tangent x plus c. The problem is, of course, c could be anything I want. But by saying I know a value, this is sometimes called the initial condition. By saying I know a specific value of y, for example, when x is pi force and y equals 1, that lets me say something about c. C is no longer arbitrary. In fact, what does c have to be? Well, this has to be true. So what I'm going to do is I'm going to plug it in. So y of pi force equals 1 says that 1 has to equal 2 times tangent of pi force plus c. What is tangent of pi force? It's 1. By the way, this is very useful to know that tangent of pi force equals 1. At some point in the near future, it might come in handy. I'm not saying anything. I'm just saying it's good to know. 1. So this says 1 is 2 plus c. So what does c need to be? So c has to be negative 1. So I know it's some antiderivative. By knowing the initial values, I can say, aha, I know exactly which one it is that you're looking for. You're looking for y equals 2 tangent x minus 1. All right. Okay, well, you guys need a long weekend to study, so we'll stop here. So the midterm goes up through what we've covered today. I have office hours next Wednesday and Friday. Don't forget to turn in your homework. Have fun.